Hi, in this video I'm going to introduce the concept of a derivative using a geometric approach. And just for starting up, I'm going to use this graph I have on the left, and I'm going to sign things here on the line on this graph. So first I have this point I'm going to call P, this point here nearer to the center, and then I'm going to call this other point, I'm going to call it Q. Now, what information can I get from Q? Now, P and Q, they are forming a secant line. This secant line is crossing out this graph in blue. I'm not naming you. I'm not telling you which function it is. I'm pretty sure you can infer it's something like an x squared, but the thing is not important. We're going to talk about a concept, so those kind of details are actually relevant for the explaining purposes. So now, what's the value? I'm going to continue with what's the value of x for P? I'm going to call it I'm going to give it a name. I'm going to call it A. So if the value of A it will stand for the value of x for P, the value of y would be for y, f of A. I'm sorry. Now I'm going to name this other point on the right of A. I'm just going to use a different letter, and this letter will stand for this difference of position, which will be letter H. So in other words, this point here will be the value, will have the value of A plus H. So applying the same logic we used from the previous when we use P, we talk about P. So for Q, the value of Y will be F of A plus H. Now we know these things P and Q, we have their values for H, for X and Y. We know they form a secant line for this that crosses out this function in blue. The thing is, we're going to try to get to the concept of the derivative by using an approach that were used basically back in the 17th century. And back then, the guys were concerned with the concept of velocity and a particular case of velocity. But we're going to start by using what we know from the physics course of velocity. We learned over there what's the velocity. So velocity is basically a final position minus a initial position over a final time minus a initial time. I'm sorry, this is very ugly. Okay, initial time. And well, there was this guy, they were very concerned with this concept of velocity, and this guy was Sir Isaac Newton. I'm pretty sure you should remember him. In case you don't, I'm going to introduce him to you. Isaac Newton was something, this guy with curly hair, and okay, and there it is. There we go. There it is. Isaac Newton. And let's try to make it smiley. There it is. And well, so this guy was concerned with this concept of velocity, but not exactly with this only velocity. He was concerned with the concept of instant velocity. And so, well, instant velocity is basically the concept of the thing. What is the velocity of an object that's moving in a particular moment of time? So in a particular moment of time, a specific moment of time, the difference between the initial and the final position will be a zero, because the final and the initial position will be the same. And so you can say with the final and initial position. So if we have the difference of position, I'm going to write difference of position like this. This is this small triangle stands for the Greek letter delta. It means difference. So difference of position over difference of time, and if we got that these two are ended up being 0 over 0, we know what it is. Well, what's that? We know that it's undefined and it's really something really bad. So you remember there. And well, actually Newton saw it. He saw it like this. He saw it. So and he tried to find a way to solve this truth, to get past through this undefined here. So the way he did it was actually very confusing, to be honest. And so we're going to use the way they solved this other mathematician solved in more into the 19th century, because I think it's far easier. So the thing is, we're going to focus on what we know, and here it is the thing. We know we have this graph and we have this secant line that passes through P and Q, and the question is, the instant velocity will be concerned with the fact of what happens when Q gets really close to P. Now, what happens when you move from here, from A plus H, and you move to A over there? That is to say that the value of H will get really close to 0. So I'm going to show you in a graph how will this look like. There it is. Here is my graph in Desmos. I'm using the same one from the I'm showing you, and this one's animated. So I'm going to show you what happens when you get this point Q. I'm moving it, and this point Q, where it gets really close to the other one, P. So we can see that we move from a secant line, it's clearly a secant line, and then when it gets really close to each other, there it is. It transforms into a tangent line. We move from a secant line to a tangent one. Here is a tangent line. So now let's get to the mathematics behind of it. Now, so we know that the slope of a function, of a line, we know it's a difference in y over difference of x. In other words, will be final y minus initial y over the final x minus the initial x. So I'm going to work through with the information we have on the graph. So in other words, the final y will be the y for q, and the y for q, we know it's f of a plus h. So I'm going to write it in here, f of a plus h. So the initial one will be the other one, f of a. So it will be minus f of a. It will be all over the final x. The final x will be the x for q, which is a plus h. Be a plus h minus the initial x, that will be that the x for p will be only a. There it is. And here we can cancel out things. We can simplify things out. This positive and negative a, we can simplify them out. So we get to this. It'll be f of a plus h minus f of a. And this will be all over h. And the question we're raising here, what happens when the value of h gets really close to 0? Luckily, the thing is, we have learned how to treat these mathematical problems. We use the concept of a limit when h approaches to 0. And the thing is, this is the concept in mathematics that is called a derivative. And I'm just going to mention, there are several notations for this derivative. I'm just going to mention the first one we're going to be using would be like this. It's called f, it's read as f prime of x. And for this video, this will be all. This is just an introduction to the concept of derivative using a geometric approach. Just try to remember basically the last statement and try to understand through all these. Remember Newton and the undefined. Okay, let's continue with an example.